So last week we began our unit 6 unit on thermodynamics and kinetics, basically the idea of heat and energy and reactions. And what I said is that this marks the transition, unit 6 through 8. We technically have a unit 9, by the way, in this entire curriculum. We're not going to make it. Okay. We're just not going to make it if I want to give you any exam study days. I might do a mini lesson in unit 9 with a quiz, but it's not going to be the full lesson, which is unfortunate because I spent a lot of time actually building it out last year for the hope of making it this year. But alas, we have not. So, anyway, this marks the start of a very macroscopic look on chemistry, a lot more applied chemistry versus just particles. Now, you're still going to look at how do we explain the macro from the micro particle level, but we're still focusing more on shifting our eyes toward the macro experience. All right. And right now we're looking at speed. How do we control the speed of a reaction? This will eventually shift into how do we understand energy in reactions in general? Because like speed of anything is highly connected to the energy that's associated with it, right? So we're going to start transitioning after this, but what today we're going to do is we're going to solidify your understanding of chemical kinetics and how collision theory and the 4 factors that we can deduce from collision theory help us understand how we control the rate at which a reaction happens through a flip-a-clip project. Okay, so I'm going to, yes, you have today and tomorrow to work on it. A lot of you guys are quite masters at flip-a-clip, and for those of you that are not, did you do flip-a-clip in Halfrek? Perfect. Just making sure he didn't like last minute change that project. We will have today and tomorrow to work on it. And if you were not here last week, so Min and Drea, if you were not here last week, you will spend the day getting yourself caught up to hopefully get to the point where tomorrow you could work on flip-a-clip during class. But if not, it will be a take-home project for you to do. Okay. But the plus sides is I don't think it requires internet. I don't think at home. No, it doesn't. Okay. So the plus side is that you can do it at home while you're babysitting or watching TV or whatever. Okay. Probably not cooking though. Don't recommend that. So let's do a quick review on what does collision theory say. So what was one of the principles of collision theory? What could someone describe me one of the principles? One of the 2 big ideas behind collision theory? Yes. Yes, you need to have your particles. So a reaction occurring, how we even see a reaction happen, why does that work? Like other than the fact that we have to combine these 2 things under this category of type of reaction, like why does that happen? Why? Because you know that reactions occur through 1, contact. That's the whole principle of collision theory. And 2, they occur because those particles collide with enough energy to sufficiently break. Last time, Min and Drea, we were talking about how just because you bump into someone doesn't mean you break your arm, right? You have to have enough energy. So not every single point of contact with somebody means that you're broken afterwards, right? But with the same is true for particles. So particles, they collide in a given amount of space, but not every single collision actually meets the qualifications to create a new reaction or to create a new substance through bond breakage and bond forming. So the first principle is that not only do you have to collide, but you have to collide with enough energy. What do we call the minimum amount of energy that's associated with meeting that quota? Yes. The activation energy. It's the energy amount necessary to activate reaction occurring. And the energy, how do you calculate the activation energy? It's where you start from, wherever potential energy your reactants start with to the hill they have to climb, the peak of the climb, okay? The peak of the max energy you need. And it's the difference between those things that give you your activation energy. It's kind of like saying you're going on a hike and you start at 6,000. That's way too high. You start at 200 feet above sea level, and then you climb 1,000 to 1,000 feet above sea level. You would say that you climbed 800, right? You don't say, oh, I climbed 1,000. No, you started at 200. So you climbed 800 more. Same thing with chemistry and how we read energy changes. That's going to matter in a little bit. That's why I'm starting to tell you this now. Okay. So what was the second postulate or kind of principle that goes along with collision theory. Not only do they have to collide with enough energy, but Howie, they have to collide in the correct positioning. Notice bigger molecules, you could break that up at any point. Like, why do we break it up exactly here? Well, it's because orientation or positioning of the particle collision is super, super important. If I want to break your arm, but I hit your leg instead, maybe I hit your leg with enough force, but I wanted to break your arm. So I had the wrong place. So I would have had a failed mission. Okay. Same thing is true with particle reactions is when they collide, not only do you want them to have enough energy, you want to put the energy in the right place so that when you break the bonds, the ideal bond formation occurs in the right locations. Thank you. So pretty standard, honestly, kind of intuitive in a lot of ways, but guess what? Somebody won a prize for writing it in a postulate. Somebody got a lot of money to make that conclusion based off of various lab tests and experiments to confirm it. Drea and Min, what I was saying last week is that one reason why collision location is so important is it explains a lot of the reasons why in reactions we get side products that have never been discovered. Like when I was doing my research, I made a ton of unknown molecules that have never been made before because the particles would collide and break in the wrong places. Now, why didn't I win a Nobel Peace Prize on it? It's because I couldn't remake them. They were totally accidental. I couldn't figure out a way to like isolate that process happening exactly the same. It was just a random collision point that happened to break at that place and make something else. But it wasn't reproducible. So that's why those particular side products didn't win me anything. But a lot of chemistry is based off of accidental side product collision, side products from accidental collisions in the wrong locations. And they were able to reproduce it in a controlled manner. I was not. And I didn't want to. They weren't that important of molecules. But anyway, that's a big thing. So then from those two postulates, what were 4 ways we can speed up a reaction and how so? What's the relationship? Mika? Increase surface area. Okay, for which particular state of matter does that work with? Stay at solid, liquid, or gas? Solid. Solid. So increasing surface area, and what do we mean by increasing surface area is not just dumping it into a bigger container. What we mean is we literally grind up the powder so that the specific group of particles is easier to interact with another group of particles. It's kind of like saying it's harder to make sure that, let's say we all huddled into a group. Whoever's in the center of the circle, dances, mosh pit. You can't, what's the likelihood of the people in the middle of a mosh pit getting in contact with the outside world? Not much. They're so far in the middle. So what if we spread everybody out? That increases chances of interaction if people can mingle, okay? Same thing with particle surface area for solids. If it's ground up into a powder, a mortar and pestle use, kind of like a guacamole bowl, where you grind everything up, it is much likelier to have more collision statistically, therefore much likely to have more reaction completed, okay, or carried out. What's the other one? So increase in surface area for solids increases the rate of reaction, increases the likelihood of collision. What else? Well, there's 3. Lachlan? No. Whoa. That was awkward. I just looked at you. Liam? Huh? Stirring. Agitation. What's the relationship between rate and stirring? Excellent. So you increase the kinetic energy, your kinetic energy transfers in to the particles, wherefore you're also increasing the statistical encountering of the particles together, and more of them are going to meet activation energy minimum, so you're going to get higher rate of reaction, more successful collision through stirring, or agitation is another way to put it, right? Nothing like agitating a roommate or friend and to get a reaction, eh? So what was the third one? Aislinn? Temperature. Temperature is the cheapest and easiest, most reliable way to control up and down the rate of a reaction. What's the relationship? Give me one of them. As temperature increases, rate increases. It's because Temperature is technically a measure of kinetic energy. So if we increase the kinetic energy of all the particles in a sample, you're going to increase collision and you're going to increase the force of which the collisions occur at, therefore more of them meeting activation energy. On the other hand, oppositely, or contrarily, if you decrease energy, you could slow down a reaction, right? It's one reason why you freeze your food. You literally slow down the reaction of your meat or your object of chosen item from decaying, which is a type of chemical reaction. There's a decomposition that occurs with your food. If you can slow that down by putting it in the freezer, that's really helpful for your wallet and for society to not have food waste. Hi. So what is the last one? The one that is the most effective. Yes. Adding a catalyst, it was not mentioned yet. That's the fourth and final way that you can increase the rate of reaction. And this is the most effective way. The problem is it costs more money because you add in another chemical, like what we did with our demo, the pink cobalt chloride catalyst, right? We saw that we get it at the beginning and we get it back at the end, but then it gets used up in the middle somehow. It disappears. Okay, that's what a catalyst does, is it changes the mechanism. It often produces temporary compounds that promote the overall reaction that we want. But then it comes back to us at the end. So it's like overall net, it wasn't used in the reaction. But it's kind of like when you put in bumper rails up on your bowling game. You can put them up and you can put them back down. And the overall net is that your ball went down and hit the pins. But it comes in during the process and it helps prevent your bowling ball from going astray. Same thing with catalysts. They change the overall mechanism so it makes it easier. So if you want to take the hill analogy, instead of climbing Mount Kilimanjaro, the one pathway, it's like if someone gave you an escalator up. You still end and start at the same places, but your way of doing it is totally different and way easier, way less energy. So catalysts change the overall activation energy by changing the pathway. Most effective, but more expensive, and usually catalysts tend to be more toxic elements. Transition metal-based catalysts are really common. Okay, so that being said, I want to introduce to you guys your project. So hopefully you can find this on my website. You have the notes from last week. You're welcome to look them up. I also taught you a really quick conversion between Celsius and a new unit of temperature called Kelvin. But we're going to switch over to just getting you guys into saying it in your own terms. So either pick up a physical copy of the collision theory assignment or download via Canvas for me, please. So this is what you should have picked up or downloaded. All right, it's a flip a clip project related to collision theory. What you guys are going to do is you're going to explain the demo, that initial phenomenon I showed you. You're going to explain it, okay, using collision theory via flip a clip. And so this is pretty self-guided. It's not too complicated, but I do want exact correctness in your explanation. So on the demo, which you can totally see, I filmed it in the recording of the lecture. I filmed the demo in the recording of the lecture, so you can find it. It's toward the beginning anyway, so you don't have to watch too long. What we did is we decomposed hydrogen peroxide into water and oxygen gas. And we timed it originally at 50 degrees Celsius, and it was really nothing was happening. Then we raised the temperature. We saw, well, I saw it better because I was right here, but we saw some gas evolution, which told us that, oh, the reaction was happening. If I'm seeing gas be produced, that means that I'm producing O2, which means the reaction has been happening. But then we added in the pink catalyst and it went cray. It started bubbling and the color started changing and all that good stuff. And we basically thoroughly transitioned hydrogen peroxide into all this vaporized oxygen and just remaining colored water in the beaker. Okay, so what you're going to do now is you're going to explain that from a particulate level using collision theory. what was happening at the particle level to explain why temperature, one of the factors experienced and tested in the demo, and adding of the catalyst, one of the other factors experienced and tested in the demo, seemed to increase the rate of reaction. And of course, the catalyst increased it far more effectively than the temperature. So what you're going to do is you're going to create a flip a clip that explains all of this. And the flip a clip can be anywhere from a minute to 2 minutes. I really don't think it needs to be longer than 2 minutes. I highly doubt so. And I also wouldn't expect it to be less than a minute because I don't know how you would get the information in otherwise. Last year, people that did like 30-second videos, I docked them off. I was like, you did not explain this well enough. Big idea is what you're going to do. And this is kind of the order it probably should go in, but it doesn't have to. I just think this makes more sense. You're going to introduce the reaction and you're going to introduce collision theory in general, the two principles. And then you're going to talk about the reaction specifically. So what's going to happen is I'm going to break the bonds of H2O2 and I'm going to make new bonds to form water and oxygen. You're going to tell me, based off of collision theory, what were the two factors that we addressed? Okay, temperature, increase of kinetic energy to meet activation energy, and catalyst, okay, changing the actual pathway, lowering the activation energy. And you're going to talk about those two factors separately and their relationship with the rate of reaction because they each produced a change in rate. Okay, so I want you to address the rate one at a time. And obviously, you probably want to mention that one method was way better at affecting the rate than the other. Okay, and you're definitely going to have to use this vocabulary down here. If you're not using this vocabulary, I don't really know what you're saying. That is very scientific. You could describe this like any person on the street, like, bro, it went really fast, like cray. Okay, but that's not what we want. Here, you're going to do a more professional presentation of collision theory explanation with specific relevance to your demo. Okay. And then, of course, you have your walkthrough video and so forth. You're welcome to show me it beforehand so that you know you're on the right track, and that's very helpful. It also makes grading easier for me and my TAs. And then, of course, my big thing is please download when you do finish into movie or MP4. It does not work if you submit it directly from Flip a Clip. I can't open it through Canvas. I can't do it. So you're welcome to work in a partner, but I do not want a group of 3. It's unnecessary. So I would personally think this is actually low-key easier to actually just do it alone. There isn't like a different molecule you're doing. It's kind of one solid explanation. It's not like you can really break it up that much. So, and I am expecting audio description. So that's all I have to say. And best of luck, everyone. That's your project. And you'll have today and tomorrow to work on it.